Semiconductors. What are semiconductors? Semiconductors are neither good conductors nor good insulators. What that means as far as atoms of a semiconductor or atoms of a material, inside the atom, same as any other molecule, you have a nucleus where you have neutrons and protons. Neutrons are electrically neutral, protons electrically positive charges, and around them you have orbits of electrons which are orbiting around, and they're all negative charges of electricity. Now, the number of electrons on the last layer of an atom, if it is more than 4 electrons on the last layer or last shell, then you're going towards a good insulator, and if it's less than 4 electrons, you're going towards a good conductor. Whereas if it's 4 electrons on the last layer, then it's a semiconductor. When you increase the temperature of semiconductors, the electrons become excited and move to a higher layer or higher level or shell, which improves the conductivity, which is called intrinsic semiconduction. These free electrons are called minority carriers. The two most common types of semiconductors are silicon and germanium. We can improve the ability of these materials to conduct electricity by adding other materials, which we'll call impurities. When we do this, by adding impurities to either silicon or germanium, we call that doping the material. That action is called doping. And this makes electrons the majority carriers, with the holes being the minority carriers. So for instance, in this type of a molecule, if you look at the atoms here, this is an N-type material with a spare electron on the last layer, which is a donor atom, or a good donor. This is a phosphorus molecule, part of the molecule, and this is the atom of the phosphorus material. Now, this one is the atom. Inside here, you have the atom of a good acceptor, because you have a hole here, a spare hole, rather than having a spare electron, extra electron, free electron. You have an electron missing, which is a spare hole, which makes it a good acceptor atom, such as boron. And this is a p-type material. This is a mistake here. It should be p-type material. In short, some semiconductors can be formed by doping intrinsic silicon and germanium with impurities. N-type material is formed by adding material that has a spare electron or a pentavalent material. P-type material is formed by adding material that has a spare hole or a trivalent material. Examples of doping material will include pentavalent material, arsenic, antimony, phosphorus, trivalent material, boron, aluminium, indium, gallium. One popular semiconductor that's used in electronic world is diode. Diode is a semiconductor with this symbol. One side, this side is anode, and this side is cathode. This side is the negative side, this side is the positive end. Usually in real life, it's like something like that with a number typed on it. For instance, 1N4001, and you have a line, a band here on one side, which indicates the cathode pin, and this pin is anode. Basically, it's formed of two types of semiconductor material. One side is p-type, one side is n-type, and they're joined together. Then you've formed a region which is called depletion region, because you have on one side extra electrons and one side extra or spare holes. Now, the way they're joined together is a technology. They use special technology to join them together. But as they join, you form a depletion region here, which is basically between 0.6 to 0.8 volts region. You need that much voltage to cause these electrons, spare electrons, to jump across to the holes or fill the holes and cause electricity or flow of electricity in the circuit. And it basically acts like a one-way valve in mechanical engineering. So it's a one-way valve, and electrons go from one side to the other, and it won't go the other way backward. And that is called forward bias. When you connect the diode in this format, where the p-type is connected to the positive end of the battery, n-type is connected to the negative end of the battery, then in actual circuitry, you would be looking something like this, but we're looking at inside of the diode. The depletion region, as soon as the voltage, if the voltage is more than that amount that you need to break through the depletion region, which is 0.6 to 0.8 volts, then these electrons from the N-type will jump across and we will have a flow of electricity. And then obviously if you have a lamp here, for instance, or a load, then that will turn on. But if the battery was the other way, this is called forward bias mode. And if it was the other way around, then it wouldn't work. What happens is if the battery is backward, what I mean by that is the negative end is connected to the P-type side of the diode, and the positive is connected to the N or cathode. So negative is connected to anode, positive is connected to cathode, the wrong way basically. And this is called reverse bias mode. And what happens is basically you have spare electrons here and you have spare holes here. With the power of the battery, you're actually increasing that depletion region, that barrier. So you won't have any current going through the circuit. That only happens up to a certain amount of voltage. If you apply a big amount of voltage, depending on the type of the diode, then you get to a voltage, like for instance, for this type of diode, when you get to 400 volt in a reverse bias, then you have a breakdown. Well, that is called breakdown voltage. Then you have a reverse bias current, whereas the forward bias current is this. You only have a leakage of current up to 0.6 volts, and after that, then you have a full flow of current going through the circuit. If this is voltage and this is current axis. Now, there's a different type of diode which is especially made to actually operate in the reverse bias mode. This type of diode is called Zener Diode, and they are basically designed to operate in the negative or reverse mode. On the forward bias, they won't do anything. It'll be just the same as any normal diode on the forward bias mode. So you still need 0.6, 0.8 volts before it conducts. But with this, you have a set value of voltage. You can have 10 volts, 12 volts, Zener diode working voltage, and at that voltage, it's usually used for fixing the voltage or regulating the voltage, supply voltages. It's usually used in adapters that you have for mobile chargers and laptop chargers, all those kind of things. The next thing that we need to talk about is rectification. Basically, what that means is you're converting AC to DC. So if we consider this AC sinusoidal or sine wave, full sine wave, this is our time axis and this is our voltage axis or current, voltage and current. We know about this. This is an AC. If your voltage alternates or your current alternates between positive and negative, then that's an AC source or supply. It doesn't have to be this shape. This is a sinusoidal waveform. It could be a square wave. It could be a sawtooth waveform. It could be all sorts of waveforms. But if it doesn't alternate between positive and negative, even if it goes up and down, even if it's the same shape as this, but it's only on the positive end like this, or on the negative end like this, it's just wiggling around there. It's still a DC. It's not an AC because it's not alternating between positive and negative. But it's not a good DC. A good DC, a perfect DC, would be a straight fixed line, like a battery. So now what we want to do is we want to get from AC to DC. So the first thing you can do is apply AC to a diode, and then from that you get to the load or the output. So this side is your input, this side is your output. See what happens. We said if this end of the diode is positive, it conducts. If this end is negative, it goes into a reverse bias mode, so it doesn't conduct. So what happens now with an AC waveform coming, when it comes, the positive half cycle comes in, this diode works in forward bias operation and conducts. So you'll have the positive end, positive half cycle to the load, to the output. When it gets to the negative half cycle of the supply, this diode operates now in negative bias mode, because this end is negative, that end is positive. So it doesn't conduct. So you have a gap with 0 voltage coming to the output, and then carry on again, the same cycle happening. Keep doing that. So you'll have bumps with gaps in between them. And that is called half wave rectification, because you're only rectifying half a wave and you're losing half. This is turning the AC to DC, well, it's not a very good DC. First of all, you've lost part of the AC and it's varying. It's not fixed voltage. But industries use these as voltage drop, voltage reducers. So because you lose half a cycle, you're basically dropping voltage to half. Then you can see in some equipment things like maybe you can, if you have an electric blanket, you'll see in the switch one diode is used, and that is because they want to have like two settings of heat, full heat and half heat, something like that, or motors, for instance, they have full speed or half speed. So that's still useful. Then we get to full wave rectification. Now we can do this two different ways. You either use a transformer and two diodes, a transformer with a center tap on the secondary. This is the primary, which is connected to the source, and this is the secondary, which has got a center tap as well. This is a special transformer, and it's compared to normal transformers with no center tap, it's more expensive. But you use this with two diodes. What happens here, if you apply the AC here, you split the sine wave. One sine wave will be the exact same as coming in the primary, and the other one, the other half of the transformer, it'll be exactly 180-degree opposite. So here you'll be starting from negative and going to positive, rather than starting from positive going to negative. That gives us the opportunity to use two diodes to have this type of DC on the other side. So you have full wave rectification. How that works is when this side is positive, this side is also positive, this side is negative. So this diode is in the reverse mode, is switched off, and this diode is forward bias mode and is switched on. So one diode is on, one diode is off in the first half cycle. So when it's on, the current comes through here, goes through the load, the thick bold arrows, if you look at them, goes this direction going towards down to the center to complete the circuit. And then when the other side, the negative half cycle comes, this one is switched off now because it goes into reverse mode, and this one is turned into forward bias mode, so it turns on. And then if you follow this type of arrow, a little brighter arrow, it goes through the load again the same direction. So you have positive half cycle for the first half cycle input, and then second half cycle again for the second half the cycle that came in the primary. So basically we turn both half cycles up to the positive end of the output into the load. So that's, again, cycle repeats, and you'll get all positive bumps. And obviously you could put the diodes backward that way facing, and then you'll get bumps at the bottom if you wanted to, but you just learn one way or the other. So this circuit basically is turned a full AC to full DC full wave rectification, but it's still a varying DC. It's a DC, but it's not a very good DC. Another way to do that without the use of center tapped transformer is use of bridge diode. A bridge diode consists of 4 diodes connected in this format, and you apply the AC supply to the middle points of the bridge, where you have anode on one side and cathode on the other. Cathode on one side, anode on the other, you see. And then the output is where you have both anode sides, it goes to the negative end of the load, and both cathode sides of the bridge goes to the positive end of the load. Again, how that works is it's a lot cheaper because you don't need that transformer anymore, that special transformer. And then when the positive half cycle comes, this diode is in forward bias mode. This one is switched off, so it goes this way. And it can't go that way because, again, this is switched off, so these two are switched off. And then it goes through the load. If you follow the arrow, the bold arrow, it comes back here, and it has to close the circuit to the source. So it won't go that way. It'll go through this one to the load, to the source. And then if you follow the negative half cycle when it comes, then this one is switched on, that one is switched off. So, when the next half cycle comes, which is negative, then it comes from here, negative, this brighter arrow, if you look at that, then this one is switched on, this one is switched off. And what happens now, it goes through so this and that is switched off because they are working in reverse bias, and this will be turned on. So at any half cycle of the supply, you'll have 2 diodes switched off, 2 diodes switched on, and then next half cycle the other 2 will turn on, the other 2, the previous 2 that were off, now they'll turn on. So there's always going to be 2 off, 2 on, which is good also for cooling down the diodes. So the current comes through the load the same direction and goes back to the source through this other diode back to the source. So that's how it works. The same with the bridge diode. You get positive bumps, varying DC voltage on the output. Now, we want to convert this to a fixed voltage DC, a straight line. One of the components that we can use to do that is a capacitor. When we use a capacitor, if you just ignore the other 2 elements, this is a resistor and this is a Zener diode, and that's the load that we have to begin with anyway. So if you just use the capacitor here, usually electrolytic capacitor where you have polarity, positive, negative, you have to observe that. Then what happens, as the voltage increases to the maximum, the capacitor charges, almost fully charges, and when the voltage is dropping down, then the capacitor feeds into the load, helping the source basically. So you'll have an effect called ripple effect. So you'll have some sort of a waveform like this. So it's fully charged, discharging into the load, charging again with the next bump, discharging to the load, charging again, discharging. So that's how you get the ripple effect. Now we've got now from the full AC to full wave rectification, and then to this ripple effect DC. Now we want to convert it to a full fixed DC. Next thing we want to use is a Zener diode. And this resistor is just there to limit the current, so it's not actually giving the load or the Zener diode a shock to burn it. In this case, they've used, for instance, 7.5 volts. 7V5 means 7.5 volts Zener diode. So at this 7.5 volts, anything above that, it'll basically short it to the ground and fix the voltage at that 7.5 volts. So you have a fixed voltage. So this is how you convert AC to a full fixed regulated DC. I have another video that actually simulated this circuit using multisim. You can watch that. Then we come to another device called transistors. 2 different types of transistors categorically, either NPN or PNP. This is a symbol of a transistor, an NPN transistor, and this is a symbol of a PNP transistor. This is the inside of the materials inside of the transistor, PNP or NPN. Now, we have 3 pins on each transistor. The middle one is called base. The top one usually is called collector, and the one with an arrow either going out or going in this case, is called emitter. So what it does basically, you can use transistors either to switch things on and off like a relay, or amplify the current or voltage. Emitter emits basically electrons and collector collects them, base controls it. Now, to identify whether this is an NPN or PNP without the diagram like this, then you have to look at the arrow inside. If the arrow is pointing out, it's an NPN. You could consider that as a diode, the shape of a diode without that line on the cathode side. So this side is cathode, so that's N. Then the middle one is P, and that's N. However you want to consider it, or you want to just memorize it. If the arrow is pointing towards the inside of the transistor or the base, then that's a PNP transistor. You could basically consider these transistors as 2 diodes connected face to face or back to back. So if they're connected like this, in case of NPN, then that's how they're connected. So how it works is that if you consider those NPN material inside the transistor, and these are 3 pins coming out, base, emitter, and collector. You connect this collector emitter to a big voltage, bigger battery, and between base and emitter you have a smaller voltage. The voltage between base and emitter has to be big enough to cause a flow of electrons between these 2 PN material, which is a diode basically. So you have to make this a forward bias connection or configuration for this to have electrons coming here, and then from that, the bigger voltage here and material voltage here will absorb all that instead of them all going there. Some minority will go through there, but majority will be absorbed here. So you'll have a flow of big current going through the collector emitter. So that is by convention. No, in reality, it's the other way. But it doesn't matter which way it is. It's a flow of current between collector and emitter, or emitter and collector. So with a small amount of current to the base, you can control a bigger amount of current between emitter and collector. That is the principle. So for the mechanical analogy of that transistor, it would be similar to this. You have a big pipe of liquid, of water here, and it's branched off to a valve here, and then you have leverages here to open the valve. If you open this tap, this will, the flow of water, a small flow of water or liquid will bring this lever down and push this up and open the gate or bigger valve. So you'll have something like this. A small current here or a small flow of water here has caused a bigger flow of current or water flowing here. That is basically the principle of a transistor operation. The pin arrangement for transistors are in various shapes and types. Some of them are like this. You identify them that way. For instance, this one, the two nearer this base chassis is emitter base, if you look at it this way, and this one notch indicates emitter, and middle one is base, the other one is collector. So you have different various ways of identifying base, collector, and emitter pins. And worst comes to worst, you have a data sheet for all of these transistors, which will tell you where those pins are, or which pin is what. So transistors as a switch. Transistors can act as a switch, same as a relay. If you remember a relay contact, for instance, this one, we have a small voltage to go to a push button where the operator is working. We don't want to give, for instance, 240 volts, 230 volts to the on operator's hands to be unsafe and dangerous. So we apply a little voltage, maybe 12 volts. That doesn't shock anyone, doesn't give anybody any shock or harm. So that once it's pressed, the magnetic field around this coil magnetizes and attracts a rod here, and then it connects all these contacts, and obviously disconnects the other ones. So you have connection, and then you have 230 going to the load, 230 volts, which is totally separate, electrically separate from the push button. Same thing in a transistor circuit. We can use a transistor to do almost the same thing. So for instance here, although the voltage is the same, but you're only using, if you use this 6 volts, you're dropping it with 10 kilo ohm here, and you have an LDR, which is light dependent resistor. This circuit basically, what it does is it's a street light, if you like. It's the same as street lights. When it gets dark, the resistance of this changes. This LDR changes by the light or the brightness, and you get enough voltage here. If it increases the value here, then you have enough voltage here to give to the base of this transistor. You have enough voltage between base emitter, which is, well, like we said, has to be between 0.6, 0.8 volts to forward bias the diode between emitter and base and emitter. And then you have a transistor that goes into saturation mode or conduction, or basically switched on mode. So emitter, basically, you can consider it as emitter is connected to collector as a short, like a short circuit. So if you when there's enough brightness or darkness, if you like, depending on how you configure this transistor and this circuit, then you get enough voltage here, it switches on, and that will switch on a bigger lamp, bigger voltage lamp.
All right, now we want to demonstrate using appropriate software, which is multisim in this case, how both NPN and PNP bipolar, or just general transistors, basically bipolar junction transistors, can be configured. First of all, how they can be biased or connected in a circuit to act as a switch and to operate an LED to turn it on and off. And also talk about the bias of the transistor as to how they're connected, the collector pin, base and emitter are connected in reference to the battery and the LED or the load, and how they operate in a circuit, and compare them with each other. So this, now what I've done, I've built two circuits. One is a PNP and the other one is NPN. This arrow in the transistor indicates like a diode. If you consider that as one part of the transistor, diode part of the transistor, this end, which is the anode part or the positive, is inside, the cathode is outside. So that is P, this is N, so NPN. So this is an NPN transistor, and the other design is the opposite. You can see the arrow is pointing towards the base. So the base is negative, which is the cathode side, and anode is on the outside. So anode is positive, or P, N, P. So it's a PNP transistor. This is how you determine whether a transistor is an NPN or PNP, with this arrow. So this is a PNP, and this one is an NPN. So I've built these two designs here. If I go back out a little bit, so you can see the difference. First of all, I just operate these two circuits and simulate them, so you can see how they work as a switch. Any transistor, this is just the principle to show you how any bipolar transistor would work or act in a circuit as a switch. So what we've done, if I go to the first one, NPN, so this is an NPN transistor. We've picked this type, and the collector is connected to the load, which is an LED, and is connected to the cathode part of the LED. The anode part is connected through a resistor and an emitter to the positive part of the battery, which is 12 volts. And then that positive also is connected through a bigger resistor and a switch and the emitter. The emitters are there just to show you the results in the end. So they don't have any resistance realistically in a real life. Even if you set a multimeter or amps or emitter, then the internal resistance is negligible. You can ignore them. So a bigger resistor, much bigger resistor here, to reduce the voltage, that 12 volt, to really low voltage. We only need the voltage between base and emitter to be about 0.6 to 0.8 volts for this transistor to switch on. For any transistor to switch on, that is the range between 0.6 to 0.8 volts, depending on the types of the transistors. Whereas for the collector, we only use 500 ohms because this LED is capable of tolerating 12 volts, and so only limiting the current a little bit so you won't burn it out. Emitter is directly connected to the ground and negative part of the battery. Now, when we switch this on or simulate the circuit, at the moment, because the switch is off, this base switch is off, the current through the load or LED is off, so there's zero current going there, 0 amp, and the LED, as you can see, is off, is turned off. The current through the base is also 0. Showing some values here is probably getting it like it's a simulation, although it's a simulation, but it's showing you would have some residual current going there because of the voltage induced into it. Now, if I turn the switch on, then you can see the current to the base is 75.5 microamps, very tiny, minute current going to the base. but the current going to the load, and you can see the LED is turned on, is 17, almost 17 milliamps. So a minute current to the base has controlled a bigger current to the collector of the transistor. That's the principle of transistors. Basically, you apply a tiny current to the base and you control a bigger current in the collector part of the transistor. So you basically switch on and off, and what's happening inside the transistor, you basically, it's a short circuit between collector and emitter once it's turned on. Once it's turned on, this side of the battery transistor, this side of the diode or LED is connected to earth and is turned on. Now when you switch it off, obviously there is no current going there, it's not saturated, so it's off, and there is a cut. Basically the circuit is cut between collector and emitter, and so there is no current going to the, and you can see the current is reducing. It's just a residual current or induced current that's going down to nothing and then eventually to zero. For this transistor, which is an NPN, and this is the way it's connected. Now if I compare this with a PNP, just remember where the battery is. The negative is connected to the earth and the emitter side of the transistor, and also collector is connected to the cathode of the load or the LED. Where I go to this one, it's opposite. The positive is connected to the emitter instead of negative, and collector is connected to the anode part of the load or LED. And also the base is now, this in this case is negative. The negative side of the battery is connected to the base through the resistor. The same size resistors are used, and also the negative is connected to the earth. So it's just basic, almost flipped. The circuit is flipped if you consider this and compare it with this one. And if I just stop the simulation on this one, so remember this is positive connected to the base and the collector through the load, and the load, the cathode part is connected to the collector of the base, this transistor, and emitter is connected to the ground and negative. Whereas here in a PNP transistor, remember PNP, positive, negative, positive. So positive has to be connected to positive, negative, the base is connected through the resistor to the negative, and the again positive is connected to the positive end of the load, and the other side is connected to the other side, because this LED has to have a negative and has to close the circuit, so through the resistor is connected to the ground or the negative side of the battery. Very simple, and I'll simulate this for you as well to see. Again, the same thing applies. So when I turn the switch on with a minute current of 75 microamps, 75.463, let's just say 75.5 microamps going to the base, it's switching a bigger current of 16.963, or let's say 17 milliamps current, which has turned this LED on, as you can see. So the LED is on now and it's off now, on, off. So with a small current, you're controlling a bigger current on the collector side. Whether they're NPN or PNP, they do the same thing. The only difference is the bias of the transistor. So the difference between this and that in operation, there's no difference between them as far as the operation. But as far as the configuration of the circuit, how they are connected or how they're biased, the PNP is this type, this side. The emitter is connected to the positive because it's P, and then N the base is connected to the negative, and then again P positive is connected to the load, positive end of the load, and then the other side is connected to the negative end of the battery through the resistor, obviously. Whereas the other one, NPN, N negative is connected to the ground and negative of the battery, P, the base, is connected to the positive, and the other end of the collector, N, is connected to the negative of the load, but the other side has to be connected to the positive. So that is the configuration or bias of the two NPN and PNP transistors, and the comparison as far as configuration and as far as operation. As you can see, there's no difference between the operation of the both. People use different either NPN or PNP depending on the circuit as a whole. They might have a bigger circuit. You don't have just this. You might have a complicated circuit or a network, and it depends on what you have on the rest of the circuit, or what type of supply you have, and what type of other transistors and devices you have. Then you decide whether you want the NPN or PNP, and also you consider the load as well, whether your load needs an NPN bias, a positive switch, a positive supply switching on and off, or a negative supply switching on and off. That's a big decision maker, basically. That's a big thing to decide whether you want to switch the positive to the load on and off, or the negative. That is one of the things that you first look at to determine whether you need a PNP or NPN. That is basically the comparison between the operation and the configuration between the NPN and PNP transistors in a circuit acting as a switch. This is a light sensing circuit. As you can see, there's a transistor here, an NPN transistor, which is configured in emitter, common emitter connection. Basically, emitter is common between input and output. The input consists of two resistors, two basically voltage dividers. One of them is an LDR, light dependent resistor, and this resistor is just to limit the current. These two resistors, one of them is a light dependent resistor, so the resistance of the resistance changes as the light changes. And this one is a fixed voltage. Both together divide the voltage of 6 volts. Supply voltage is divided depending on the size of this resistor at any given time, depending on the lights, you know, how much light you have. So you have a certain amount of voltage coming here, and then that voltage will be applied to the base through this resistor. And this resistor is a 10 kilo ohm resistor, just to reduce the current so you don't burn the transistor. This current is current of the base. We call it IB. This voltage, we consider this as V in, or voltage of the input, where the voltage is divided by these two resistors, V in. And the voltage of the output is connected to a buzzer, and this buzzer basically gives you the alarm as to whether there is light or not, where, you know, this is light sensing switch. So transistor is acting as a switch when there is enough voltage here, which depends on the light. If there is enough light, there will be enough voltage here to turn this on, and once it's on, collector and emitter short circuit. Basically, that's the operation of transistors. When the transistor switches on, you basically short circuit, ideally, collector and emitter, and then you have current going through the buzzer, and the buzzer operates. So that's the operation of the circuit. Now what it's saying is the resistance of the buzzer is given 300 ohms, and it says if the LDR, which is this, has a resistance of 2.5 kilo ohm or 2500 ohms at 200 lux. That's the brightness. Show by calculation if the transistor is saturated at 200 lux. Calculate the power dissipated in the transistor at 200 lux. Again, so first of all, we have to determine the value of V in, voltage of the input, this voltage from the ground to the center part of the voltage dividers. That will cause the transistor to just enter saturation. So first you need to understand, if you haven't learned that one, you need to understand what saturation is. Saturation is just what I just explained. When you have enough voltage for the base of the transistor to switch this transistor into an on mode, stat, so that the stat of the transistor will change from off to on. And at that point, basically, emitter and collector, these two pins are short. They join together, basically. So that's saturation. So what we're saying is, what voltage do you need here to turn this on, turn this transistor on? Again, another thing that you need to remember from transistors is that what turns a transistor on, because transistor has almost two diodes inside it, and we know for a diode to forward bias to operate, to let the current flow through it, you need at least 0.6 to 0.8 volts, between 0.6 to 0.8 volts between the anode and cathode of the diode to allow it to operate, be forward biased, and let the current through. The same applies here in a transistor. So you need, between base and emitter, which is the diode basically, you need about 0.6 to 0.8 volts for this switch, for this transistor to switch on. So if we consider that, then we can do the calculation. And remember, the HFE also is given 200. The HFE is a gain of the transistor. That means basically how much you're amplifying the current of the collector, which is this one, IC we call it, and IB is the current of the base. So current of the base is your input, current of the collector, IC, is your output. IC over IB is your HFE, and that's given us 200. Now, if we find one of them, then we can find the other. So if we find IC, then we know how much IB should be, then we can find the voltage. It's all Ohm's law, basically. Just the transistor here, it might just throw you out a little bit, but all it is, if you consider this as switched on mode, then these two are basically, these two pins are short, and then you can find the current here. Voltage here is 6 volts, 6 volt supply over 300 ohms when the buzzer is on, when the transistor is on, because at that point this pin is connected to this pin. Basically, there is, you just imagine as if this transistor is not there, there's a wire here. So 6 divided by 300. So if you go to our calculations, and we have this circuit just copied here. So the HFE is given 200, and that is the formula for that is IC over IB, collector current over base current. And we can find the collector current by just dividing voltage of the supply 6 volt over RL, which is the load resistance, which is that buzzer 300, and that's 0.02 amps. Now from this, if you put this in this formula, transpose it for IB, then you can find base current. IC over HFE will give you 0.1 milliamps for the current of the base. That's how much current is going through this resistor to the base. So now we have the current through the resistor. If you times this by the resistor, then you find how much voltage you've dropped here. So 0.1 milliamps, that is 0.0001 amps, you have to convert that to amps, times the resistance of the base, RB, will give you the voltage of the RB, the resistance of the base, the voltage that's dropped across the resistance of the base, which is 1 volt in this case, 1 volt. And the resistance was, remember, 10 kilo ohms, so it's 10,000. That's where this 10,000 comes from, because the resistor was 10k. So now we know this is 1 volt you've dropped here, and we know for the transistor to saturate you need almost 0.6 to 0.8 volts. So we just consider the average 0.7, then we can find out voltage of the input voltage, which is voltage of the voltage drop across the resistance of the base, PRB, plus voltage of the base emitter. If I go back to the circuit again just to show you, so to find this voltage from 0 to this point, then you need to find how much voltage you've dropped here, which we found it was 1 volt, and how much voltage you need between these two. That is basically Kirchhoff's rule. You add all the voltage drops to find the voltage of the supply. So this voltage we consider it 0.7 because we said 0.6 to 0.8 volts is needed to turn the transistor on or turn it into saturation mode. So 1 plus 0.7, 1.7 volts is our voltage, input voltage. Show by calculation if the transistor is saturated at 200 lux. So we want to see if at 200 lux, which gives you 2.5 kilo ohm or 2500 ohms here, have we got enough to turn this on? First thing you do, you find the current that goes through this branch. At 6 volts you have here, 6 volts, 2500 here, 1000 here, so it's 3500. 6 divided by 3500, that is the current that goes through this LDR. Now if you times that current, which is going through this resistor as well, by this 1000 ohm, then you find this voltage, Vin. Now we're finding it that way basically. Initially we knew we wanted this on, so we considered that 0.7, and we just to find out how much voltage you need to turn this on. That was 1.7 volts. But now we want to see at this 2500 ohm, which is when you have 200 lux. Do you have enough voltage? Do you have enough voltage to turn this on? So you have to go from this end. So 6 divided by 3500 will give you the current that goes through here. And then times that by this resistor, you find the voltage. And then you determine. So current of the LDR is 6 over 3500, which is 1.714 times 10 to the power minus 3 amps, or you could say milliamp, this much milliamps. And voltage of the input, if you times that by that 1000 ohm resistor, then you have 1.714 volts at the input. So the input voltage is 1.714 volts. Therefore, because it's greater than what we calculated here, 1.7 volts you need to turn this on, and at 200 lux you have 1.714 volts, so it's greater, so it does turn the resistor on. Now then it says how much is the power of the transistor dissipated in the transistor, not the load, transistor. So when the transistor is saturated, the voltage of the input is 1.714 volts, but the voltage of the output, because it's switched on, is 0. The output voltage between collector and emitter is short, so it's 0 volt, therefore power is 0 watts. So ideally, this is ideal though, in an ideal world, the power that's used when it's switched on is 0. But realistically, really, there is some power dissipated here because you have heat and you have a voltage between base and emitter, and so that current is still going on, and that diode is constantly on, the diode between base and emitter. So it is using some power, but the power on the output side is 0. Now that we solved this circuit, we found the IC, IB, and the voltage of the input, voltage of the output, and the power. Now we want to know if we use this circuit as a daylight sensor, like we have in street lights. You know, they're night lights. They have night light sensors. But imagine if it was opposite, daylight sensor. So now evaluate the transistor's ability to operate in this circuit. If this circuit was used as a daylight sensor, what would you recommend to resolve this issue? Now the issue with this, if we had the light here, and as the light dependent resistor changes value, and the transistor will switch on and the light will come on, and it switches off when the transistor, again, the resistor changes value. So it's a daylight sensor. When it's daylight, it turns the light on. When it's dark, it turns it off. It's opposite to the street lights. So how would this operate? The transistor would get hot and eventually will burn out. It's not a good design for that kind of application. The reason is because there's always going to be some leakage. Like I mentioned earlier, there is going to be always a voltage and a current going through base emitter, and that base collector also is switched on, is short but still current going through it, and it just heats it up, and eventually it burns the transistor. So the solution to that would be using a comparator device. So the solution to that would be using a device called comparator, or operational amplifiers, op-amps. Op-amps for short, or operational amplifier. This is a symbol for them. This is an inside of a chip. This is the chip. Basically, this is the inside diagram, and this is the symbol. What it is basically is a device with two inputs. One of them is positive input, and the other one is inverting input. I'm not going to go into details of this because I have another video about that in full detail, how to bias this, how to configure it, how to design it, and how to make this work. But basically, what it is, if you give it a base voltage, a reference voltage to one of these pins, and use another pin as an input, which could be in this circuit the light depending resistor coming into, let's say, the input 2 or input 3, it doesn't matter. If the voltage is slightly bigger than your reference voltage, let's say your reference voltage is 12 volts and your light dependent resistor gives it 12.1 or 11.9, then you'll have an output. As soon as the voltage is different, you'll have an output 1, which is the digital binary output. And then you can use that to turn the light on or off. In this case, because it's digital and it's binary, then there is no leakage of voltage. It's either on or off. There is nothing in between. It's not analog. Transistors operate in analog mode. This is a chip, an op-amp, operational amplifier, and it operates in a digital mode. So as soon as the voltage of the input, one of them is bigger than the reference, only slightly or even smaller. As soon as it's different, then it gives an output. Now, whether you want, again, a positive output or a negative output, then it depends on, depending on that, you use either the negative input or the positive input as your source of sensor, the light depending resistor will be connected to either positive or negative. So this would be the solution for that.